I'd love to see Charles with a buzz cut.
I would. My ears would look even bigger than they already are. Yeah. What do you mean? Yeah. What? Don't get buzzed? Don't get buzzed?
No, I'm just saying your ears would look good.
This
is like fact, okay? I feel your pain, man. You get rid of this one.
I really don't care.
I think you do.
No, not with the hair. Not with the hair.
All right, so let me explain why that turned into a debacle yesterday. So, if you keep in mind what you are going to have on the test, which is this equation sheet. So if you look at the form that they have given you, which is RT times the natural log of, or E naught cell times RT NF over times the natural log of Q. So this is what's actually on your equation sheet, okay, and which is what you're going to have on the test. Now, why they just don't simplify this baffles me. So if you put in the ideal gas law constant of 8.314 joules per mole Kelvin, and if you put in standard temperature of 298, and you put in Faraday's constant, which is one of the things we're going to talk about today, 96,500, and then N is the number of electrons. If you do natural log, you actually get this value, okay? So on the test, if you actually take 8.314 times 298 divided by 96,500, this is what you get. Now, if you get nerdy and you take, for example, like the log of 10 and divide it by the natural log of 10, there's a ratio that exists. So if you prefer logs, then that's that 0.0592 over n. So mathematically, the only thing that varies is the constant that's in front of it. So if you want to just get used to using what is on your sheet, because that's what you're going to have, just realize if you plug in these numbers, that's the number that you're going to generate, and why they just don't give you that in a simplified form is absolutely beyond me, but they want to be jerks. So there you go. So that's the difference between the two of them. Okay, so today we're going to talk about a concept known as Gibbs free energy. So if you look at the guy that came up with this, literally, okay? So here is Josiah Willard Gibbs, okay? It looks like an old fudgy. What is this slash campus? Now, understand when he did his work. So he was born in 1839, died in 1903. So he actually died before we found any of the subatomic particles. So ironically, he passed away before the major breakthroughs in chemistry were developed. So to give you some idea of the impact that this guy had, so Einstein did his famous work on relativity and Brownian motion and all this good stuff, and like between kind of 1910 to 1920. So Einstein did his work after Gibbs had passed. So, but Einstein said that when he had studied the works of Gibbs and the influence that he had, Einstein says he was the most brilliant mathematician and physical chemist that he had ever known after he studied his work. So this is what Einstein says about this guy. So that's a pretty good, hey, thing to say. Like Einstein says, I'm pretty cool. That's up there. So when you look at Gibbs free energy, and we're going to spend a lot of time talking about Gibbs free energy. So if you look at this green sheet, okay, on the thermodynamics section, you're going to see 4 different equations that involve Gibbs free energy. So let's talk about what that actually means. So the reason that it's called Gibbs free energy is because of the fact that if you set up a cell and you have like copper and like one we've dealt with before, and you have zinc, and you hook that up to a voltmeter and you have your salt bridge, those electrons are going to move. You're going to have a current. Now, this work was done, again, they understood the concept of cells. They didn't necessarily understand what was going on because nobody had found electrons, protons, or neutrons. So they didn't really know what was going on, but they knew that something was going on. And so because that current is moving, if you hook that up to, let's say, for example, a small light bulb, you can use that electricity to make a light bulb glow. So the reason that it's called Gibbs free energy is because of the fact that it's basically free. All you have to do is build a voltaic cell. You hook up, the electrons are going to flow, they didn't know that at the time, and you get basically like free energy. You don't, and now again, this was when you looked at the time span in which he lived in the 1800s. At that point, if you wanted to heat your house, you could burn coal, you could burn wood. Electricity at that point wasn't a viable option, okay? Nobody had, maybe New York City at that point, maybe kind of started to electrify, but certainly the vast majority of the world, if you wanted to heat your house, you burned coal, you burned wood, you burned some type of hydrocarbon. So for them to be able to say, hey, we can have electricity without having to heat up water, that was kind of a cool idea. It's like, what do you have to do? I would just have to drop things into a solution. And so that's why they were willing to consider this to be free energy. So I'm just going to hand out lecture notes to kind of summarize what I'm going to be going over. Don't flip over. So stop that camera for a second.